So in this problem we have a uniform wire of mass big M and length 4L, which is bent to form the sides of a square as shown. Now in part A of the problem we're asked to find this moment of inertia about an axis that is passing perpendicularly to the center of mass of the square. So basically the axis passes through the center of the square from into the page to out of the page, or vice versa. Now, by symmetry of the square, each side length is going to contribute the same moment of inertia to the total moment of inertia. So we're just going to find the contribution of one side and multiply by 4 to get the total moment of inertia of the square about the axis. So let's call the moment of inertia of one side of the square I1, and that's going to be the moment of inertia about its own center. So we know that for a wire of length L and mass little m, its moment of inertia about an axis passing through its center and perpendicular to the wire is just going to be 1/12 ml squared, where we have m, the mass of one side length, is just going to be the total mass divided by 4. Now, by the parallel axis theorem, if we move the axis a distance L/2, so we have that each of the side lengths is a distance L/2 from the center, then that means that the moment of inertia is going to be given by I1, which is 1/12 ml squared, plus m times the distance that the axis moves, which is L/2, all squared. And if we simplify that, that is just going to be ml squared over 3. Which means that the total moment of inertia of the system, IA, is going to be 4 times I2, which is equal to 4 times ml squared over 3. And here we have m is equal to big M over 4. So 4m is equal to big M. So we get that as just big ml squared over 3. So that's our answer for the moment of inertia, part A. Now, for part B, we have that the axis passes through the center of the square and is parallel to two sides of the square. Now, here we see that for the left and right side, the moment of inertia contributions from both of these two sides is just given by, let's call that I1. So that's going to be given by, for each of these, the expression for the moment of inertia of the wire rotated about its center. So that's going to be 1/12 ml squared. And the moment of inertia of the top and bottom side, which we'll call I2, well, we can treat them as point particles focused on their center of mass and their distance L/2 from the axis of rotation, which means that their moment of inertia is given by m times the distance from the axis, which is L/2, all squared. So if we simplify that, that's just m L squared over 4. So now we just have to sum up the contributions of each side. So the moment of inertia, IB, in part B is going to be 2 times I1 plus 2 times I2, which is equal to 2 over 12 ml squared plus 2 over 4 ml squared, which is equal to ml squared over 6 plus ml squared over 2. I think that's right. So 1/6 plus 1/2. And that is going to give you 2 over 3 little m L squared. And remember that little m is big M over 4, so that's equal to 2 over 3 times big M over 4 L squared. Which means that if we simplify this, the moment of inertia in part B of the wire is going to be big M L squared over 6, which is just half of the moment of inertia we found in part A.